Hello, my name is Matthew Nealon, and this is video 3 for homework assignment 1. And in this video, we are going to calculate the pressure forces on a cylindrical side and the spherical side of a barrel that is filled to a certain level of fluid at a fluid height of h with a radius of r. So to begin, we will get up and just kind of draw a rough sketch of what our barrel is going to look like. So our barrel will start off with our spherical side or our circular side, excuse me, and it will have a fluid height from up here. So a couple things we can just immediately label. Let's take a brevity. With this, we want to say that our negative y-axis, our axis, is our positive h. So we're going to say that this is our h, and then all the way up here, at this dot up here, it is going to be 0. So that is our sort of correlation with height. We can now say, and we can also say that this radius at this point right here is r. We can also draw out the rest of this and try to give a dimension, at least some dimensions to this barrel now. So we will draw out our dimensions as such. We'll go out to there, and then we'll go out to there, draw over. We also have sort of just a bisected area. And why we need this little middle section, I'll show you in a second, is that we are now going to find sort of like a cross-sectional area that exists at this point. So we're going to bring this down, and this is going to be sort of our cross-sectional area, and then we're going to have the rest of the end of our barrel come out like this, stop there, circle around, and end there. Kind of a rough sketch, but you can get the premise of what we're trying to work with. So we kind of have our normal shape of the barrel, with each side being our kind of acting as like our whole barrel acting as a cylinder, and we have our fluid height. So what we need to do now is take things in terms of our pressure. So what we want to do now is say that this little side up here, that the way this cross-sectional area sort of increases up to our fluid height is called our DH, or the change in our fluid height, and our length of the actual barrel itself will just be L. Because we're now going to find at least these are the two forces I'm trying to find right now, is that our force acting on this circular end and this force acting on one of our sides. And that's all we're just trying to find right now, because if we find those two, we can technically find the forces acting on the whole barrel itself. So just to begin, we want to find our cross-sectional area, or the way in which our cross-sectional area is going to change. So it's going to be our dA, or our change in A, is going to be equal to the length times our change in height, which is dH. So this is our expression, just how our height is the one that's going to determine how our area is going to change. So now what we want to do is now find our forces. So we find our forces is equal to an integral, which is going to be the sum of all of our cross-sectional areas times the pressure, which is just a little workaround of what our normal pressure equation looks like. So we're going to have our change in area multiplied by our pressure. And we can't really put terms on this yet, because we need to expand this pressure value into its longer form, which is going to be we're going to expand both of these into its longer form, and then we now have a new expression of L, our length, times our pressure equation, which is going to be density times gravity times height times dH. And if you already know, from what you can see already, we know that h is going to be our value, or not our value, our variable of integration. So we can immediately say that h is going to be our top value, and 0 is going to be our bottom value, because we're going to find the difference between these two heights. So doing this just normal basic integral, we can find that our force for our cylindrical side, because that's where our side going out, is just going to be equal to our length times density times gravity times our height squared over 2 to the height of h and to our height at 0. And since 0 is just going to cancel out the whole side of the equation, its side, it's going to be, this whole equation is just going to be equal to our length times our density times gravity times our height divided by 2. So this is going to be our equation for the forces that are acting on our on our cylindrical side, or that's going to be acting on our side, or our longer side, and not the spherical side. Now this is where things get a little more complicated, because where we need to find pressure and how we're going to find our pressure values, it's going to be a little bit more complicated with this, because cylindrical area is obviously, you can find cylindrical area with 2 pi r, or pi r squared, excuse me. However, one thing we need to worry about is how our fluid height interacts with our radius and all the other dimensions we're going to do right now. So to get started, we are going to just draw our face here again and just label all the things that we know. So draw this here. We have just a radius. I'm just going to draw 2 radiuses here. So that's a radius, and we also know that our fluid height goes up to there. That's our fluid height. And just one other thing we also know, that we do know, is that this section above the radius is actually going to be our height minus the radius, because that distance between our fluid height and our radius, we can then find, if we have both of those values given, we can easily find that little section right there. So how do we go about doing this? One thing we can do right now is we're trying to find how that pressure is going to interact with this face here. So one thing we want to do now is find how far, this fluid height is going to rise. So the way we do that is making sort of a pseudo right triangle and having this spot up here be theta 1. That is going to be our first value of theta. Let me draw that a little bigger. Theta 1. And one other thing we do know is that this theta value, at least where this radius is drawn, is going to be theta is going to be equal to 0. And since we're just going to solve for this half of the equation right now, and I'll explain that in just a moment once I get all of these equations written out, is that we're going to go down to our last theta value, which is going to bisect this circle, is going to be negative pi over 2. And this is where we can now begin in trying to find how our forces are going to interact. So we're going to find this height right here. And how we do that is just a simple way of finding x and y components of a right triangle. So we can immediately say that this little section here is equal to our radius. Let me draw this a little, let me write this a little bigger, it's a little small. Our radius sine theta. This little height here is our radius times sine theta. However, it's a little odd right now is we don't know our theta 1 value, but we do know our distance between our radius and the top of the fluid height. And we can find our theta 1 value by simply taking the inverse of our sine, or arc sine. So theta 1 is going to be equal to, I'm going to need more room. Let me just draw it down here. So theta 1 is going to be equal to arc sine. And since we assume that these values are going to just going to be given and they're not going to be changing, is that our y component, our y component, which is going to be our height minus the radius over radius. And that's going to be our angle at theta 1. So what do we do now? So what else can we do right now? So we can just simply say that our fluid height is going to be the radius plus our r sine theta, because that's how far that little distance is going to be. And we can just sort of substitute our h minus r into r sine theta, and those two expressions are equal to each other. So now what I want to do is take things in terms of what we did over here, is trying to find our dh value. So we can then take the derivative of this. It's going to be our dh, which is just simply going to be r cosine theta. So that's our dh value. However, we kind of run into a little bit of an issue. What about our x values and how the rest of these things sort of push on to this surface here? And how we do that is trying to find our change in cross-sectional area or our change in area. So how can we find this? So just to begin off, we kind of do the same thing as we did over here. We try to find sort of a length or a width that we can do, and then we try to find out, and then we have a change in height. And luckily, what we did so far is that we found our change in height, but we don't have a width or a length to work with here. However, we do in fact have a length or a width to work with. Is that it's kind of the same way we did up here with r sine theta. We know that our x value is going to be r cosine theta, because that's going to be our x. That's going to be our x component. And the way that this is going to interact with each other, that is going to be our r cosine theta. This, and how this is going to work is that it's the same thing with our sine, is that when you plug an angle or radian into our theta value and multiply it by sine, that's going to vary in length. That area is going to vary depending on where that distance is going to be throughout this circle, throughout this sort of half of the circle here. So with these two things, we can immediately say that our d theta, our change in area is equal to our radius times cosine theta times r cosine theta. And since we're trying to find things in terms of our theta value, we need a d theta over here. So as you notice, they're exactly the same thing, which makes it really easy for us to find our our force is going to be acting on it. So what we're going to do now is now take all of our terms that we've found and then multiply it out into an integral to get from one integral to an, excuse me, so we're going to take all of our terms and then we're going to put it in an integral and multiply it out, going from our theta 1 value down to our negative pi over 2 value, and that's going to get that that force acting on that portion or that half of the circle. So we can now say that our force is going to be equal to 2, or yeah, it's going to be 2 times density times gravity. And the reason why we need a 2 here is because our this only takes in terms of one portion of our circle. So we need to take both sides. So we multiply this whole thing by 2, and then we have our integral, which I said before. So we're going to start at theta 1, or we're going to end at pi over 2. Let me just erase this. I need a little bit more space to work with here. So right now we have our force equal to 2 times density times gravity. Then we have an integral, which is going to be our negative pi over 2, our n value, and it's going to be theta 1. So what goes in this integral? So we multiply this out, we're obviously going to get r squared times cosine squared theta. So we already know what one of our terms is going to be. However, we need to multiply it by the height, which is, we already know is going to be r plus r sine theta. So from there, we can then multiply all this out. So we're just going to get this in its base form before we start multiplying out or doing in the more complicated integrals. So what we can get here is that our r plus r sine theta. I am writing these things very small, unfortunately. So let me do this one more time. R plus r sine theta multiplied by r squared cosine squared theta d theta. And then we can multiply these terms out to get this. Our force is equal to 2 times the density times gravity times negative pi over 2 times theta 1. And then we can multiply both of these terms out. So we're now going to have our radius cubed times cosine squared theta. We don't want parentheses right there. Plus our radius cubed times sine theta times cosine squared theta d theta. So this is going to be our sort of huge integral that we're going to find that's going to end up leading to our force value on our cylindrical force. So just to get this a little further along, so we're not doing crazy calculations when we actually get the integral, we're going to have our force is going to be equal to force up here is going to be equal to 2 density times gravity. And if you notice here is that we have a radius cubed. So we can immediately take that out. It's because that's going to be a constant no matter what, because it's radius. So we have r cubed, and then we can now take sort of integrals of each of these sides. And since just normal integral rules, we can take two integrals, one of our r cubed cosine squared theta plus the integral of our not our r cubed, but our sine theta cosine squared theta, both to d theta. So we're going to have a new integral that looks like this. So first, we're going to have that, and then we're going to have our first integral, which is going to be our pi over 2, 1, which is going to be our, let's just start with our sine cosine theta, because that's going to be a lot. We're just going to organize it as such. So it's going to be, so this is going to be sine theta cosine squared theta and then we have our next integral, which is going to be our cosine, our simple cosine squared theta, d theta, d theta. Shove both those in. So that's going to be sort of our expanded, that's going to be our expanded form. So now what we want to do is come back over here and then sort of multiply this out so we know what's going to go on before we go to our final integral. So our forces, so it's 2 times theta times gravity times our r cubed value. I'm going to have our negative pi, or now we don't need this anymore since we're going to start doing our integral. So right now, we are going to end with our theta over 2 plus our 1/2 sine theta cosine theta, and that's going to be to the negative, excuse me, that's going to be to the negative pi over 2, and then theta 1, and then under that, we are now going to have our integral of this, which is going to be 1/3 cosine cubed theta, and that's going to be to the points of negative pi over 2 to our theta 1 value. And this is our final equation, and then once we're able to plug in all of our, once we have sort of like a given value list, then we can find our total forces that are acting on each side of this. So we have our first one over here that's going to be acting on our cylindrical face, and then this one over here is going to be acting on our circular face. So this is going to be our total force. It's going to be acting on our circular, and we already have our cylindrical